Working on the homework for 12.1, double integrals over rectangles. Here's number 13, skipping 11 because it's straightforward. This one's pretty straightforward also. We've got our integrand contains a product of two functions. One is a function of y completely, and this is a function of x completely. So this is one of those special cases, actually. I could, if I want, split this up into two integrals, and it's kind of a little shortcut. I could do this. I can make this equal to, first I grab the function with the x's in it, which would be e to the 2x, and I do that integral, and then look, the limits of integration on x are 0 to 2. Then I can multiply that times the integral from 0 to 4 of the function of y. Now you can only do that when these two can be separated by multiplication, and that this is completely a function of y, this is completely a function of x. I could do that and then work them out and be done. What I'm going to do though is do it the other way, because it'll work both ways, will give you the same answer. I'm just going to go start with the inner integral, figure out what that is, and then integrate that after I get that answer. So integral 0 to 2. So what is the antiderivative of this with respect to y? Remembering e to the 2x is just a constant. So the antiderivative of y cubed is going to be 1/4 y to the 4th. But then we still have the constant here, e to the 2x. I'm going to evaluate that at 0 and 4, and remember, since we're integrating with respect to y, this is y equals 4 and y equals 0. So dx. So what I'll do is I will go in, I'll replace y with 4. So we get, let me see here, I can fit this here. Integral 0 to 2, bracket, I'm going to have two things here. So when I plug in 4 for y, I get 4 to the 4th. And then when I divide that by 4, it's really 4 to the 3rd. So 4 to the 3rd is 64. And so I have 64 e to the 2x. And then when I plug in 0 for y, I get 0. So now I'm just integrating, continue this up here. Integral from 0 to 2 of 64 e to the 2x and dx. Now I can ignore the 64. The antiderivative of e to the 2x is 1/2 e to the 2x. So antiderivative of e to the 2x is itself, but then you have to scale out by 2 because of chain rule. So I get this equals, remember I said 1/2, so half of this is 32, e to the 2x, and evaluated x equals 0 to x equals 2. Plug in 2 for x, we get e to the 4th times 32, minus, plug in 0 here, e to the 0 is going to be 1 times 32, so minus 32. So that should be it for number 13. Now, again, you could do it the other way, and you should get the same answer. Let's take a look at 17. Looks interesting. Integral 1 to 4, integral 1 to 2, x over y plus y over x dy dx. Now I know I'm integrating over a rectangle because of my limits of integration. So like I already know, I'm just stating this just to state it. I already know that my x's are between 1 and 4, and my y's are between 1 and 2. So I know I'm integrating over that region right there. Okay. Now, I cannot do what I did in the previous problem because I don't have a product, and this is a mixture of a function of x and y together, same with this. So even if that was a product, well, if it was a product, it would be 1, but even if it was a product, if you got x's and y's mixed up in both the functions, then you can't use that shortcut. So I'm kind of stuck to do this as is. All right, well, let's take the inner integral, work on that. Now, what I think I'll do before I actually do the integration, I think I'll rewrite this as x times y to the negative 1 plus y times x to the negative 1 dy dx. So all I did was rewrote this. Okay, brought the y up, brought the x up. That'll help me a little bit with the antiderivative. So this will be equal to integral 1 to 4. Now the antiderivative of this with respect to y, the x is a constant. The antiderivative of y to the negative 1, since that's really like 1 over y, is natural log y. So I'm going to get x times natural log the absolute value of y, and then plus, now the antiderivative of this right here, again, this x thing is a constant. The antiderivative of y is 1/2 y squared, but then times the x. And I'm evaluating this from y equals 1 to y equals 2 dx. All right, let's go ahead and plug in now. So if I plug in, still have this integral out here. I'm going to have an inside, the inside here, but going to have something minus something. So first plug in 2 for y. You get x times natural log 2 plus, you plug in 2 here, 2 squared is 4, half of 4 is 2, 2 times x to the negative 1. And then now let's plug in 1. So if I plug in 1 for y, natural log of 1 is 0, so that's gone. Plug in 1 here, we get 1/2 times 1 times x to the negative 1. So that's just going to be 1/2 x to the negative 1. Okay. Now we're going to integrate this. So let me do that right here. This equals, I'm wondering if, the only thing I'm considering is whether or not we should put these two together because they're like terms. They're both x to the negative 1. Let me do that. This would become x natural log 2 plus 2x to the negative 1 minus 1/2 x to the negative 1. These two together become 3/2 x to the negative 1. So what I'm going to do is I'm going to integrate 1 to 4 of x times natural log of 2. Guess I'll just leave it like that. X times natural log of 2 plus 3/2 x to the negative 1. I'm integrating this with respect to x. So I get this equals. All right, so natural log of 2 is a constant. Antiderivative of x is 1/2 x squared times the constant that was there. Plus, here, this is like a 1 over x. So the antiderivative of 1 over x is natural log. So I have the 3/2 natural log absolute value of x. I'm evaluating this x equals 1 to 4. Okay, let's plug in 4 here. 4 squared, 16, half of 16 is 8. So I get 8 natural log 2. If I plug in 4 here, I get natural log of 4 times 3/2, so plus 3/2 natural log 4. Minus, I plug in 1 here for x. I just get 1/2 natural log 2. Plus, and then plug in 1 right here, natural log of 1 is 0, so 0, that's gone. All right, this is looking kind of weird, but I'm going to leave my answer in exact form. So let me see, I've got 8 natural logs of 2 plus 3/2 natural log 4 minus 1/2 natural log 2. Now, I could put these two together because they're both natural log 2, so I could combine those. Let me do something here, see if this makes sense to you. This 3/2 natural log of 4 is the same as 3/2 natural log of 2 squared, because 4 is 2 squared. Property of logs, I can drop this out in front, multiplication. It'll cancel with this 2, and I just get 3 natural log 2. So I have 8 natural log 2 plus 3 natural log 2 minus 1/2 natural log 2. So just combine all the coefficients. 8 plus 3 is 11, take away 1/2. So we're doing 11, we're taking away 1/2, common denominator 22 over 2 minus 1/2 is 21 over 2. 21 over 2 natural logs of 2. That should be it. I'm wondering if the book has the same, yeah, they did the same thing. Okay, so there's a couple of those first ones. 21 looks kind of cool. We're integrating over this region, this rectangle R, xy squared over x squared plus 1. And then dA. Now, they give us what R is. They give us that R is, I'll write it the way they have it here. R is equal to the set of all ordered pairs, so all points in two-dimensional space, such that 0 is less than or equal to x is less than or equal to 1, and, comma, usually means and, -3 is less than or equal to y is less than or equal to 3. Okay, so this just means our domain, our x's go from 0 to 1, our y's go from -3 to 3. So that's our rectangular region we're integrating over. Here's our function we're integrating, or that's the surface that we're integrating. Trying to find basically the volume underneath that surface on top of that rectangle. All right, so because they did not tell us explicitly what order of integration to use, we should be able to use Fubini's theorem that we can choose the order of integration as long as this is a nice function, which it is because you never get division by 0. X squared plus 1 can't ever be 0. So this is a nice continuous function. So it's my choice here on the order of integration. So let's think about what we would prefer to do. Would you like to treat x like a constant, which would mean all that's a constant, and just integrate y squared? Or would you prefer to treat y squared as a constant and integrate x over x squared plus 1? They both are pretty simple integrals, right? Well, the antiderivative of y cubed, y squared is pretty easy, 1/3 y cubed. This one right here, we can do a basic substitution. If u is the entire denominator, then the derivative of that is up here. So we could, well, it's off a little bit, but we could do it. So both integrations are pretty easy, but I'll go with y first because it looked like the easier one. So that means I'm going to have dx on the outside. I'm going to do dy in here first. Xy squared over x squared plus 1. And since x is on the outside, that means my outer integral is going to go from 0 to 1, the inner one from -3 to 3. All right, let's go ahead and do that inner integral. Antiderivative of this with respect to y, we said again, all this is a constant. So we just get 1/3 y cubed times all that. So I'm going to just put 1/3 y cubed times x over x squared plus 1. We're evaluating this from y equals -3 to y equals 3 dx. All right, so we're going to come in, we're going to replace y with 3 first. All right, and because of, sorry if you can hear the guys outside mowing the grass, got their blower. This is equal to the integral from 0 to 1 of, and we're going to have two things here. Let's see if I can squeeze this in here. Let's make sure that's coming out on camera. Yeah, good. All right, so let's plug in 3 for y. 3 cubed, 27. 27 divided by 3 is 9. So I get 9 of those. So I'm just going to put the 9 on top. 9x over x squared plus 1. And if I plug in -3, -3 cubed is -27 divided by 3, -9. So I'm going to have -9x over x squared plus 1. Minus a negative becomes plus, so I'm taking 9 of these, I'm adding 9 of them, I'm going to have 18 of them. So integral from 0 to 1 of 18x over x squared plus 1 dx. And at this point, I'll just do a basic u sub on this. So let's do that now. So on that problem right there, what I'm doing is I'm kind of coming over here, I'm doing some scratch work. I'm trying to find the antiderivative of 18x over x squared plus 1 dx. Basic u substitution, I'm going to let u be the denominator. The derivative of that is 2x dx. I actually almost have that. I have 18x dx. All right, so what I'll do here is put 1/2 du equals x dx. And I'm going to take this 18 and pull that 18 out, like that. So what I'm going to do is I'm going to replace x squared plus 1 with u. I'm going to replace x dx with 1/2 du. So this integral becomes 18. This right here is 1/2 du. 1/2, I'll put the du in the back because of multiplication. And this is 1 over this, so 1 over x squared plus 1, which is u. Everyone's going to have different ways of integrating, depending on who you took for Cal 2. Bring the 1/2 out, you get 9 integral 1 over u du. So 9 natural log of the absolute value of u plus a constant, but this equals 9 natural log u was x squared plus 1 plus c. So that's the antiderivative of this. But we're doing a definite integral. I was just doing that to get the antiderivative. So back over here, this should be equal to 9 natural log. I don't really need the absolute value because x squared plus 1 is always positive. But there's your antiderivative. I'm evaluating this from x equals 0 to x equals 1. And so let's plug in 1. If we plug in 1, we get 1 squared plus 1, that's 2. We get 9 natural log of 2 minus, now when we plug in 0 here, we get 1. Natural log of 1 is 0, so minus 0. So that should be it right there. 9 natural logs of 2. What number was that, 21? All right. I think I'll let you do 23 and 25. Those integrations might be a little weird, but let's do 31. 31. Find the volume of the solid lying under the elliptic paraboloid x squared over 4 plus y squared over 9 plus z equals 1 above the rectangle R, which is equal to the interval -1, 1 by the interval for y -2, 2. So this is basically my x restrictions and my y restrictions here. So that gives me my limits of integration. This is an elliptic paraboloid, so it's written as an equation. What we need to do is convert this into some function of x and y so that we can do a double integral over this rectangle of the function of x and y with respect to the area. So just solve that for z, right? We solve that for z, because normally we'd say this is our z value, right? So we solve that, we get 1 minus, I'm going to write that as 1/4 x squared plus 1 minus 1/9 y squared. There we go. Order of integration really isn't going to make a difference here because this is a well-defined function. Integrating with respect to or y, they're both pretty easy. So I'm going to just go, I'll put my x's on the outside. -1 to 1, -2 to 2. I've got 1 minus 1/4 x squared minus 1/9 y squared. I'm going to go with respect to y, then we're with respect to x. So let's integrate that with respect to y. I'll do that right here. So I've got integral -1 to 1. Integrating this with respect to y, I get y minus 1/4 x squared y. Remember, because that's a constant. So antiderivative constant with respect to y is just a constant times y. Antiderivative here, minus 1/27 y cubed. Evaluating this, y equals -2 to y equals 2. And then all of that is going to be inside another integral. Hold on, let me see what this was here. Okay. So the 2 is going to go in for y. So when we plug in 2, we're going to get two things here. Okay, plug in 2 for y, we get 2. 2 right here for y times the 1/4, we get minus 1/2 x squared. 2 for y here, we get 8, right? 8 over 27, so minus 8 over 27. Plug in -2 for y, we get -2 there. Here, -2, that's going to become plus 1/2 x squared. And then plug -2 in here. -2 cubed is -8. But then we are going to subtract, so it's going to be add 8 27ths. So let's see what happens. Looks like everything's going to get doubled up. So we have okay, 2 plus 2, 4. -1/2 x, take away another 1/2 x, sorry, squared, is just negative x squared. And then negative 8/27 minus another 8/27 is going to be a minus 16/27 dx. And I could put these together, but I don't feel like getting a common denominator. So I'm just going to do an antiderivative right now. This is 4x minus 1/3 x cubed minus 16/27 x. I'm evaluating that x negative 1 to 1. So let's plug in 1 first. We get 4 minus 1/3 minus 16/27 minus, plug in negative 1, we get negative 4, we get positive 1/3, we get positive 16/27. Everything looks like it's getting doubled up again. So we get 4, add 4 is 8, negative 1/3 minus 1/3, so negative 2/3, negative 16/27 minus another one, so negative 32/27. Looks like I have no choice but to get a common denominator here. So get a common denominator of 27. So 27 times 8, got to go old school here, 56. 16 and 5, 21, 216, so 216 over 27 minus 9 on top and bottom, 18 over 27 minus 32 over 27. So when you take 18 away from this, you get 198. 198 minus 32, 166 over 27. I can't stand doing arithmetic. All right, which one was this? 31, 166 over 27. Good. All right, so that's it for the videos on this section.